In this video, we're going to take a look at the hydrohalogenation of alkenes, which comes about when an alkene is treated with a hydrogen halide or hydrohalic acid. And it results in the addition of a hydrogen and halogen across the pi bond of the alkene to the two atoms of the alkene. So it's a hydrohalogenation since we're adding hydrogen and halogen. Now, for unsymmetrical alkenes, there's a regiochemical question here. To which carbon does the hydrogen add, and to which carbon does the halogen add? So in this example, at the top of the slide, there's really no regiochemical issue since the alkene is symmetric. I have an ethyl group over here, ethyl group over here. So whether the H adds here and the X here, or vice versa, that's the same molecule drawn two different ways. However, in general, these two groups need not be the same. And then we run into a regiochemical question about the structure of the product in a constitutional isomer sense. We have the possibility of regioisomers. To illustrate this, I wanted to consider this methyl cyclopentene substrate when it's treated with HCl. Hydrohalogenation of this substrate can lead to two possible regioisomeric products. We can recognize, first of all, that the double bond has two carbons with different substitution patterns. The top carbon is more substituted than the bottom carbon, which bears an H. We might call that less substituted. One possible regioisomer has chlorine linked to the more substituted carbon of the alkene. Chlorine linked to the carbon highlighted in blue here. But we could imagine another regioisomer where the hydrogen and chlorine switch places. Chlorine ends up linked to the less substituted carbon and hydrogen to the more substituted carbon. Now there's a rule in hydrohalogenation and other electrophilic addition reactions of alkenes that hydrogen adds to the less substituted carbon and the halogen to the more substituted carbon. This is known as Markovnikov's rule after its originator Markovnikov, the Russian chemist. The Markovnikov product is the favored product, and it has the halogen linked to the more substituted carbon. The product with chlorine linked to the less substituted carbon, or more generally the halogen atom, is known as the anti-Markovnikov product, and it's a minor product if it's observed at all, although we'll learn a method later in the course for generating the anti-Markovnikov product selectively. It doesn't involve the same mechanism as Markovnikov hydrohalogenation, which will be our focus here. When you're first starting out with hydrohalogenation, Markovnikov's rule may seem a little bit cryptic. Why does the halogen end up linked to the more substituted carbon? As it turns out, we can use the mechanism of the reaction to explain this tendency of the halogen to end up linked to the more substituted carbon. The mechanism involves a carbocation intermediate, and the more substituted carbocation is more stable and forms selectively in hydrohalogenations. That cationic carbon is attacked by the nucleophilic halide anion, and so the halogen ends up linked to that more substituted carbon in the final product. Let's see what this looks like in terms of curved arrows and reactive intermediates and the like. So the first step in this reaction is going to be proton transfer to the alkene. HCl is a strong acid, and the alkene pi electrons are mildly basic. And so through electron flow like this, we can protonate the double bond, quote unquote, and this creates a carbocation, like so. Now, there are two ways this can happen. One is shown here, with the proton ending up linked to the more substituted carbon of the double bond. But there's another way this can happen. The proton could end up linked to the less substituted carbon of the double bond, and this would produce an isomeric carbocation. So take a minute to pause if you need to, and notice these two carbocations are isomeric. They're constitutional isomers. Moreover, the cation in the top left, that's secondary. And the cation in the bottom right, that's tertiary. The tertiary cation is more stable, so in fact, we don't observe any of the so-called anti-Markovnikov product with chlorine linked to the less substituted carbon, because this would require the intermediacy of the less substituted carbocation. Instead, we see chlorine linking to the more substituted carbon because this involves a tertiary carbocation intermediate, and that's more stable. So after this initial proton transfer step, we could also think of this, by the way, as association of an electrophile, the H plus being the electrophile here, to a pi bond. After that step, chloride anion is also produced, and chloride attacks the cationic carbon in a nucleophilic attack step, and this leads to the product shown here. So the Markovnikov product is entirely derived from reaction through the more stable and more readily formed tertiary or more substituted carbocation in general. So Markovnikov's rule really, when we peel back the arbitrariness, just comes down to carbocation stability. This reaction occurs through the more stable carbocation selectively. The reaction coordinate diagram for hydrohalogenation can help us reinforce this point. The first step is proton transfer, and it's endothermic because we're going from a neutral alkene to a carbocation. And so we're going uphill in energy to generate this rather unstable carbocation intermediate, even despite the acidity of HBr. If we go to a higher energy carbocation that's less substituted by protonating at the more substituted position, generating the secondary carbocation, well, now the activation energy is much, much higher, and the stability of the intermediate is much, much less. The energy of this intermediate is much higher, and so formation of this less stable cation is negligibly slow relative to formation of the more stable cation via protonation at the less substituted carbon. After this carbocation forms, we're already past the rate-determining step, so nucleophilic attack at the cationic center is very rapid at this point. Let's practice with hydrohalogenation by predicting the product of this reaction. The first thing I'm going to notice here is that I'm dealing with an unsymmetrical alkene with a more substituted carbon and a less substituted carbon. So regiochemistry is something that I'm going to need to think about. And we can apply Markovnikov's rule here now in its revised form, where we're just going to consider the relative stabilities of the possible carbocations that would form en route to the possible regioisomers. So in hydrohalogenation, the first step is proton transfer to the alkene, forming a carbocation intermediate. This can happen two different ways because of the two differentially substituted carbons in the alkene. We could end up with a primary carbocation by putting the proton in the more substituted carbon, or a tertiary carbocation by putting the hydrogen on the less substituted carbon. And we know from considerations of carbocation stability that that primary carbocation is a no-no, and the tertiary carbocation is, at least in a relative sense, relatively happy. So the reaction will go selectively through this tertiary carbocation. And to finish off the mechanism, we want to note that we made a bromide anion in the first step. That will attack the cationic carbon, and we end up with this more substituted alkyl bromide product with none of the primary bromide observed because this primary carbocation does not even form. In this example, an achiral alkene is converted into an achiral product, but it is very common in these and other addition reactions to alkenes that new stereocenters are created at these carbons that undergo addition. In that case, the alkene is referred to as prochiral. The alkene itself is achiral, but if we were to add a fourth group to one or both of the carbons, we've created a chiral molecule. In that case, the alkene is called prochiral. And this is very common in additions to alkenes, especially with a lot of different substituents involved. We can think about the stereochemical course here by considering the relative orientations of the groups added to the alkene. They can either add to the same side, say both coming from above or both coming from below, or they can add to opposite sides of the alkene, and this leads to different stereochemical outcomes. It leads to diastereomers, in fact. When in a hydrohalogenation, H and X add to the same side of the starting alkene, we get what are called the syn products, or this is referred to as syn addition, when the two groups add to the same side of the alkene. For example, in this reaction here, the top two products come from addition of H and Cl to the same side of the alkene. In this product, H and Cl both came from above, ended up on wedges. And in the second product here, H and Cl both came from below and ended up on dashes. But the point is, in a relative sense, H and Cl are on the same side of the original alkene. This is what makes them the syn products. H and Cl could also, at least in theory, approach opposite sides of the alkene and end up on opposite sides of the alkene. In that case, we refer to the reaction as anti-addition, or the products as the anti-products. And we see that in the bottom two products, that H is up and Cl is down in this first one, and H is down and Cl is up in this second one. So both are anti-products. One thing we should point out now is that the syn and anti-products are diastereomers of each other. Notice that these two products, for example, differ in configuration at the chlorine-bearing stereocenter, but have the same configuration at the deuterium-bearing stereocenter. So they're diastereomers of each other, while the two anti-isomers here are enantiomers of one another, and the two syn isomers here are enantiomers of one another. In hydrohalogenation, for reasons we'll explore in the ensuing slides, we get racemic mixtures of the syn and anti products. So we get equal mixtures of these two enantiomers, equal mixtures of these two enantiomers, and we tend to get different amounts of the syn and anti diastereomers because they are diastereomers, but there's no consistent selectivity here for syn versus anti. No easy predictions we can make. We're going to get a nasty mixture of stereoisomers out of this reaction. The reason for this mess becomes clear if we consider the stereochemical course of the two steps of the mechanism. In the first step, we protonate the alkene, and this can occur with HX coming from above or below the plane of the alkene. If HCl, for example, comes from below the plane of the alkene, we end up with this carbocation. And if HCl comes from above the plane of the alkene, we end up with this carbocation. And these cations are enantiomers, and that's worth checking on your own, actually, that these two are enantiomers of each other. Because we started with an achiral alkene and achiral HCl, we're going to get a racemic mixture, or an equal mixture, of these two enantiomers. Protonation of the alkene occurs with equal probability above and below the plane of the alkene. Now we can take each of these enantiomers and imagine chloride anion attacking the carbocation. That can happen two different ways for each enantiomeric carbocation. Chloride could come from below, for example, and that would lead to the structure shown here with chloride underneath the cationic carbon, or chloride could come from above and form a bond above the cationic carbon, and that would lead to this product right here. We could play the same game with the enantiomeric carbocation, generating two more products. This one where the chloride, again, came from below. I didn't draw in curved arrows, but you can get the idea from here. It's the exact same idea. Chloride ends up on a dash below the plane of the screen. Or chloride could come from above, in which case it ends up on a wedge above the screen. And now, although these cations are technically enantiomers of one another, and these products end up being diastereomers, they're all very similar to each other, right? So we're going to get a messy mixture of products out of this reaction in general, with no consistent selectivity for syn and anti, since again, the selectivity here is more or less 50-50. Deuterium and hydrogen are so similar to each other that we're going to have no selectivity for chloride coming above and below the plane of the cation really at all. This slide shows an even simpler case where we don't even have another stereocenter in the molecule as we did here with the deuterium and hydrogen bearing stereocenter. In the general case of an achiral carbocation, we're going to get a racemic mixture of products, since X- will add with equal probability above and below the plane of this cation, leading to a pair of enantiomers. And the idea here again is we're going to get equal amounts of these enantiomers, in other words, a racemic mixture or racemate of the two possible alkyl halide products. Finally, because hydrohalogenations involve a carbocation intermediate, we've got to watch out for carbocation rearrangements in this reaction. If we generate, for example, a secondary carbocation that can rearrange to a tertiary or resonance stabilized carbocation, it will do so. For example, the major product of this reaction is actually the tertiary alkyl bromide, even though this tertiary carbon was not involved in the alkene double bond at all in the original substrate. To explain this, we can step through the mechanism and see that a carbocation rearrangement is going to come into play. So we first have a proton transfer. We're going to protonate to put the H on the less substituted carbon, leaving the carbocation at the more substituted position. And if this secondary carbocation were to be attacked by bromide, that would lead to this secondary alkyl bromide, but this is the minor product. A much faster process than this bimolecular reaction between bromide and the carbocation is an intramolecular, unimolecular 1,2 rearrangement that converts the secondary carbocation into a tertiary carbocation, which is more stable than that starting secondary carbocation, of course. So this new carbocation, which is very rapidly formed from the secondary carbocation initially generated, can now be attacked by bromide, and this leads to the major product which again involved this carbocation rearrangement followed by nucleophilic attack. So watch out for this. When you generate a carbocation that can rearrange to a more stable cation, that will generally occur very rapidly to give the product derived from rearrangement as the major product.